In Chapter 3, we start considering motion in higher dimensions, which means 2 or more dimensions. And one example is in Problem 1, where we have a function that describes the x motion as a variable of time and a y function that describes the motion in the y direction as a function of time. And we're asked to find the position of the rabbit, in this case, at t equals 15 seconds. So we know that x at 15 seconds is going to be minus 0.31 times 15 squared plus 7.2 times 15 plus 28. And if we do these calculations, we find out that it's 66.25, and we're told the x and y directions, right? Meters. And then we'll do similarly for the y function. And we plug in 15 for t in the y equation. And we get an answer that gives us negative 57 meters in the y direction. And now you can think of this as the x component is 66.25 meters, and then the y component is 57 negative, so it's downward. And we want to try and find the vector that deals with these two components, so we can say that our vector is given by 66.25 meters in the I hat direction plus, or minus in this case, 57 meters in the j direction, j hat direction. The magnitude of r would be the square root of 66.25 meters squared plus a negative 57 meters quantity squared. That gives us a magnitude of 87.40 meters. And if you remember from your trig or from reading the notes, the angle that this vector r makes is going to be the tangent inverse of negative 57 meters over 66.25 meters, which is the y component divided by the x component. Also notice that if you have a positive x and a negative y, you're in the fourth quadrant, so the angles there are in the 270 to 360 range. If you plug this in your calculator, you find out you get about 319.29 degrees. So this would be part A. Part B is asking what is the velocity of the rabbit. So for part B, we know that the velocity is going to be the derivative of the x function with respect to time in the I hat direction, and then the derivative of the y component of motion with respect to time for and times the j hat direction. And we can rewrite this also as, because we're taking the time derivative, we can use the prime notation or the dot notation and say it's x dot or x bar I hat plus y bar j hat, and then the derivative of the x would be negative 0.62 t plus 7.2 in the I hat direction plus the derivative of y with respect to t is 0.44 t minus 9.1, and that's in the j-hat direction. At t equals 15, we get the following, that v of 15 seconds is the same as negative 0.62 times 15 plus 7.2 in the I-hat direction plus 0.44 times 15 minus 9.1 in the j-hat direction. So this is, in other words, you can think of this part as v sub x at 15 seconds, and this part as v sub y at 15 seconds. Do this, and you get negative 2.1 meters per second in the I-hat direction minus 2.5 meters per second in the j-hat direction. So now we have the magnitude, the component, of the velocity. So v without, this is v vector, v magnitude at 15 would be the square root of negative 2.1 meters per second quantity squared plus negative 2.5 meters per second quantity squared, and that gives us a 3.26 meters per second magnitude, and the theta of this v is going to be the tangent inverse of the y component over the x component. Notice in this case you have a negative x and a negative y. That means it's in the third quadrant, which should be between 180 and 270. And if you plug this in your calculator, you should get about 220.3 degrees.